So for lesson 5, we're going to talk about the law of sines and law of cosines, and I'm going to give you one application of them. I'm not going to talk about the Heron's formula because that's going to be within your notes and you can look over. Now I will give a brief description of your notes because it does relate to the lesson task. So let's talk about the law of sines. So already I have a pre-recorded set of notes that we can talk about to make things smoother. Let's say I have this triangle where I have A, B, C, and the sides opposite from A is alpha, the sides opposite from B is beta, the side opposite from C is lowercase c. So if I decide to solve for the area, we know that from previous chapter, we can calculate the height, and then that would be written as 1/2 beta times alpha times sine of C. If I wanted to use a different angle than angle C, like if I was given a different reference angle, then it would be 1/2 alpha C sine of B, or it could be 1/2 beta C sine of A. Either or, you can calculate the area of the triangle. Now it's important, since we have 3 different ways to calculate the area, they need to be equivalent. So I can simplify this by having, or I can make an equation out of it by saying them all equal to each other. And then the key thing that I'm going to be doing now is I'm going to multiply all of them by 2 over alpha beta c. And the reason why this is still logically equivalent and everything, I'm just multiplying the entire equality like that, I am going to get sine of c over c equals sine of a over alpha and sine of capital B over beta. And remember, these angles corresponds to the side. This is the law of sines that you'll be working with. You can use this to help solve for other sides of the triangle or angle measurements of the triangle. So each of them will correspond to the opposite side for each angle. Opposite of angle C will correspond to the side lowercase c. Opposite side or angle side to angle A is alpha, and opposite side to angle B is beta. So how do we solve triangles? You need to figure out all of its side measurements and also its angle measurements. Now, you have 4 cases in solving triangles. 4 cases. The first one is angle side angle or side angle angle. If I were to give you a triangle with predetermined angle and a predetermined side in between the other predetermined angle, like so, these are predetermined or fixed, I am able to use law of sine to solve for this. I have enough information. Now, I also put the word or, side angle angle, because they are equivalent at the end of the day. But why are they equivalent? Because it says here I have a side, predetermined side, and 2 predetermined angles next to each other without any predetermined side. That's not the image that we have. However, because 2 angles are predetermined in this problem over here, this is the same as saying I have a predetermined angle, so let me erase this side. Predetermined angle, and let's say I had and then because I have 2 predetermined angles, I know in a triangle, I will have that third angle predetermined only because a triangle must add up to 180 degrees in our case. So if I have a side, I can call this angle, side. That is the reason why they are equivalent, because having 2 predetermined angles will automatically predetermine a third one in your triangles. So that's a very powerful thing. And we'll be using law of sines for that. We'll also be using law of sines for case number 2, side angle. I have 2 predetermined sides and an angle not in between them. I put a star here because this case is actually a lot of details that we need to go over. And then case 3, side angle, predetermined side, a predetermined angle between the other side. This one over here, we'll be using law of cosine. And the last one, side, we'll be using law of cosine. This is if all the sides are predetermined, but no angles are given. All right, so case 1, and I already have solved some stuff out. So the ones that I circle are the ones that I have not given you information, or erase this. I am not giving you information on angle B and what alpha is. So if I wanted to solve for alpha, and this will be, sent as in Blackboard as your notes. How do I solve for alpha? I need to relate the angle A, sine A of alpha over alpha, or sine A over alpha, and I have to relate it to something that is already given to me, both the side and the opposite, or both the angle and the opposite side. In this case, I have angle C given, and I also have lowercase c. So I can use sine of A over alpha and set that equal to sine of 25 degrees, which is capital C, over lowercase c, 80.4. And then I cross multiply. If I cross multiply, I get alpha sine of 25 degrees equal 80.4 sine of 20 degrees. Make sure your calculator is in degree mode when working with degree measurements. So if I wanted to calculate that, I just divide by sine 25 degrees and I get approximately 65.068. And that's going to be the length of alpha. And you can use that information to solve for all the other measurements. If I wanted to solve for angle B, mu of angle B, or measurement of angle B, I do 180 because the triangle sum to 180. I have two predetermined angles now. I can use that information to get the other third angle measurement, which is 135 degrees. So I can put it over here. Boom. And that's very helpful. Now I can use other information. I can use sine of 135 degree, which is capital B, over beta, and use that to solve for beta. Boom. If I use it to solve for beta, I get 135 or 134.5. And that's going to be the length measurement. So that covers for that idea. Now we go into case 2. Case 2 has 4 different options. 4 different criteria, or 4 different options, I'm sorry. The first option is if, hey, I have my 2 predetermined sides and the angle, however, they're already predetermined. There is no way for me to make this a triangle. One of the predetermined side is way too small. If I wanted to try to create a triangle out of this, it would look something like this. However, that angle that's predetermined is too big for that to even work. This is an impossible triangle. There's no solution in this case. That's one part, one option. Option 2 for case 2. Well, it could be a perfect length of alpha where I can create a 90 degree angle. And this will be, a 90 degree or right triangle where I can use Pythagorean theorem instead. So I don't even have to use law of sine. I can, but I can just use Pythagorean theorem. And then third option right here. In the third option, it's weird because there are 2 triangles, believe it or not. In this case, I have a triangle swinging this way and a triangle swinging the other way. Oops, I can't really draw it on here. Boom. Swings this way, but it's the exact same length if I swing it this way from the center. So if you want me to draw it, it'll be like this. Let's suppose alpha was this way, and I'm swinging exactly in this direction. This is alpha, this is alpha. I have 2 triangles in this case. This is the first triangle, and this is the second triangle. They both can have that same angle measurement. That's a very big deal. This means you have 2 solutions to work with, not one. You will have 2 solutions, or 2 triangles, I would say, that you need to solve for. So that's something you need to think about. And then the last one, the last option for case 2 is that what if, and this is a good example of the this is a good example of the drawing right here. Boom. It shows you that these 2 alphas are the same measurements, but they can swing either direction. And they will give you different lengths for the bottom side. And the last option is if you have one unique solution. The alpha cannot swing the other way. Because if I swing it the other way, it'll change that angle measurement that's predetermined already. So this way you have one unique solution. So let's show an example of how we can use law of sines for this. Let's say we have one solution case. Well, in this problem right here, I don't have angle measurement B. Oops, it's taking a while to load. I don't have angle measurement B, so I need to solve for angle B. Now, notice that angle A, I have predetermined, and the side opposite to angle A, alpha, is predetermined as 7 root 2. So I'm going to use law of sine to set up that ratio, and I'm going to set that equal to sine of B over beta, which is 7. So I only have one unknown, which is really nice and easy to solve. So when I solve for this, cross multiply, solve all that stuff, I get sine of B is equal to 7 root 2, or sine of B is equal to 7 times sine of 45 over root 2. I can cancel out the 7s, and I get this. Now, sine of 45, you can actually calculate that, which is really nice. You can calculate that. That's going to give you square root 2 over 2. Square root 2 over 2 divided by square root 2. And if you solve for that, simplify it out, you get sine of B is equal to 1/2. Now, if you go on your unit circle, Technically speaking, you have a y value here, you have a y over here. These both can be value 1/2. It is important when we talk about calculating sine inverse, mathematicians decided to cut off the domain and range and whatnot. That way it becomes a function. However, in the real world application, you can't always ignore those other solutions. If I told you to calculate it, yes, I want only within this domain and range. However, in a real world problem, you have to keep an account at what makes sense. In this case, I have 30 degrees and 150 degrees. So this is going to be 30 degrees. And then all the way over here is 150 degrees. And they both have that same sine or y value of 1/2. I have to be very careful. It's because the reference angles are the same. How did I get 150? Well, you can just subtract 180 to that to get that. That's the reference angle. Remember that. But that's an issue because I have two different solutions. Now, you might have two different angle measurement. However, with the one solution case, there's only one solution. How do you know if it's only one solution? Well, you have to check if it makes sense for your triangle. 150 degrees in particular, I crossed that out because if I go back to my original triangle, I have 45 degree as a predetermined angle. Now, the moment that I have the other angle measurement being, 150 degrees, 45 degrees plus 150 degrees, that's way past 180. Your triangle has to sum up to, for the angle measure, 180 degrees. So that's the reason why we have to take that away. Then that goes with case 2. Here is another set of triangle. Again, you could do this in your notes and everything. I'm just going to go through this quickly. All right. If you wanted to solve for this triangle, you would cross multiply, solve for angle B. And then, you would have sine of B is equal to this ratio over here, this ratio. If I wanted to solve for this ratio, and give me a second, boom. This is always, it's laggy, I don't know why. But if you wanted to solve for this ratio in particular, you need to use the inverse. And this is going to give you 65.8 degrees on your calculator. It's only one solution. However, when you think about it, remember, your calculator only works for that function when I cut off the domain and range. So you have to account for the other angle that has the same reference angle. How do you calculate the reference angle? You do 180 minus 65.8. If you do that, you get 114.2 degrees. So again, with that triangle, we have something over here. Boom, boom. You have to keep account for that. Now, we don't have exact measurements or anything. Do these values work? Let's look at our triangle. Our triangle, we have an angle measurement of 43.1 degrees. That means 65 point whatever does work. But that also means 114 degrees or whatever does also work. Which means we have two triangles that are solutions that we need to use and solve for. So I'm going to call this A1, B1, C1, and A2, B2, C2 triangle. That way we can differentiate them. You need to solve for the other remaining sides and the other remaining angle measurements. They're going to be different. That's the case where we have two solutions. Now, what if we have no solution? How does that even look? Well, that means the ratio inside your sine inverse has to be bigger than 1 if we have no solution. Why? Because any value bigger than 1 can be rewritten as a fraction. Or if I have a ratio right here, 3 over 2, that means your opposite is 3, your hypotenuse is 2. That doesn't even make sense because your hypotenuse is the longest side. If I had sine inverse of 8, well, 8 is bigger than 1 because 8 over 1, 8 is the opposite, 1 is the hypotenuse, and that doesn't make any sense. This is when you also have a no solution case. So that talks about law of sines. Now let's go with law of cosines. So this is going to be a 6.6 in particular. Now in law of cosines over here, I drew this little picture over here to give you an idea. Now, I use x1 and x2. So in particular, I drew a triangle ABC, and alpha, beta, and lowercase c on the xy plane in particular. I put it at the origin to give you an idea. So if I draw this pink line over here, the little heights, the heights in particular, then I get x1 and x2. I'm going to call it x1, x2 to get the idea. If I wanted to solve for the length of alpha in particular, this is the right triangle. So I can do a squared plus b squared equals c squared. Or I can do this squared plus this squared, and that should give me that alpha squared. Now I need to solve for x1 and x sub 1 and x sub 2. So let's do that. Well, x sub 1 is just sine of 180 degrees minus a equals x sub 1 over beta, because that's opposite over hypotenuse over here. Now, if you didn't notice yet, 180 minus your angle measurement or is the exact same thing as the angle measurement itself. So what I mean by that is this is equivalent over here. If I multiply beta both sides, these two are equivalent. Why are they equivalent? Because they have the same reference angle. The reference angle is the same, so they're going to have the same y value. It's like saying you have sine of 30 degrees versus sine of 150 degrees. They will be the exact same. If we're talking about sine, they will be the exact same. Now, that also holds for cosine. We just got to deal with the negatives and positives, of course. So that's just a little idea. As long as we just make it strictly positive, we're good to go. So boom. We can also do with cosine as well. So that means I can solve for x1 as beta sine of a, and I can solve for x2 as beta cosine of a. Boom. So now, going on below, to solve for alpha, we're going to have the side squared equal to that hypotenuse squared. So alpha is going to be squared, and it's going to be equal to beta sine of a squared plus beta cosine of a minus c. Where did that minus c comes from? Well, x1 is negative. It's negative. So to get the value of the entire side, I got to subtract c, and then I have to get the positive value. So x2 minus c. And this is exactly x2 minus c. But I don't have to get the positive value, because if I square it, it'll automatically become positive. This is very nice. So then I get beta squared sine of a plus, or beta squared cosine of a minus 2 beta c cosine of a plus c squared. Minus c times minus c is equal to c squared. You have to FOIL it out. You can't just square every single term. That's not how it works. And you should have known that by pre-cal algebra. And then we move to the next line. If I wanted to factor beta squared from this, I can factor as beta squared times sine squared of a plus cosine squared of a. But then the remaining part didn't have beta squared, so it didn't get factored, didn't get changed. Now, if you use your identity, sine squared of the same angle measurement as cosine squared, if I add them together, it should be equal to 1. You do need to know these identities. So that just leaves to beta squared minus 2 beta c cosine of a plus c squared. Great, we're doing good. And then if I want to solve it out and whatnot, I can just move the c squared to the other side. I get alpha squared equals beta squared plus c squared minus 2 beta c cosine of a. It's a mouthful, but it's actually easy to remember. Why is it easy to remember? This is the law of cosines. There's 3 statements you can make. These are the 3 statements, and I'll tell you why it's easy to remember. Boom. This is the law of cosine. It's very easy. So the idea is that whatever side you're working with is being squared, and then you're going to have cosine of that angle opposite, or where the side is opposite of that angle. So if I'm using alpha squared, I'm going to have cosine of A. If I'm using beta squared, I'm going to have cosine of B. If I'm using c squared, I'm going to have cosine of C. Very easy to remember. Now, the other parts are also easy. Well, I'm just squaring the other side measurements. So instead of alpha, if I'm using alpha squared, I'm just having beta squared plus c squared. If I'm using beta squared, I'm just having alpha squared plus c squared. Order does not matter, guys. Order does not. It's addition at the end of the day. So if I have c squared, it's beta squared plus alpha squared. And then those sides that you aren't using are going to be over here. Boom. So if it says alpha squared, then we're going to use beta c. If it says beta squared, we're going to use alpha c. Same things that got squared earlier over here. So it's not too bad. You're just minusing 2 of that value times cosine of whatever your reference angle is. So boom. That's what the law of cosine is. Now let's put it into practice. Let's say I have this right here. Boom. And I want to solve for this angle measurement in particular. Well, if I want to solve for this angle measurement, I think, did I give the value out? I thought I did. Maybe I didn't. I have all 3 sides. This is side, side, side. I can just set up alpha squared to solve for A. I can solve for A. That means I'm going to use alpha squared. So if I use alpha squared, I have this. Boom. Now, I got to solve for cosine A, so I have to remove everything. And removing everything, plugging in the numbers, eventually I get all the way down here to 0.953 equals cosine of A. Once I have that, I can use cosine of inverse. Now, the question is, do I have 1 solution or 2 solutions? That's the beauty of cosine. Law of cosine is stronger than law of sines. We actually only have 1 solution. Why? Because If I want to have a positive input, this is a positive value right here. This 0.9353 is positive. So if I want to have a positive value on the unit circle, the x value is positive. So it has to be in the first quadrant or the fourth quadrant. Now, unless my angle measure is negative or past 300, then I won't have those two solutions. If it's past 300 degrees, clearly it's not in a triangle. If it's negative, we don't have negative angle measurements in a triangle. So we only care about the solution we have. So law of cosine avoids having two triangle as solutions, which is very powerful. So that's for side, side, side. Now, if you have side, angle, side right here, you'd have that same case. Boom. If I want to solve for, let's say, alpha here, because I have a predetermined A, well, you set this up. Set this up for the same one. Plug in the values, solve for your variable. In this case, our variable is alpha. You will have to square root, but when you square root with the plus or minus, you can ignore the negative. The reason why is because we don't have negative distance. So boom, you can solve that out and whatnot. That's very nice. And now you can argue that you can use law of sine here. You can, but the problem about using law of sine here, you'll have two solutions and one of them cancel out. Doing law of cosine is more consistent because you don't have to worry about that issue, which is very nice. So that covers it for those kind of problems. Now let's work with an application that you might see for the lesson task. So I brought this questions from the book because I think it's very good. A pilot sets out from an airport, heads in a direction of north 20 degrees, flying at 200 miles per hour. After 1 hour, he makes the course correction, heads in north 40 degrees east. Half an hour of that, the engine trouble forces. Now, before we talk about planes and all of that, we do need to have a definition of what an angle bearing is. So, or bearing angle. Bearing angle. If you remember what the bearing angle is, it's the angle formed from the y-axis, not the x-axis. A lot of you guys drew triangles from the y-axis. That was incorrect. You have to draw it from the y-axis for the bearing angle. For a reference angle, you do it from the x-axis. This is very important. Don't make that mistake. So if I form it from the y-axis, if I have this angle measurement, let's say I have 135 degrees right here, right? 135 degrees is somewhere around here. That triangle or that angle I'm creating is right here. How do I calculate that? I do 135 minus 90 because that's where the angle here is, 90. Or I can use 270 if it's down here. I'm not using 180 anymore. I'm not using 360. For bearing angles, it's only 90 and 270. That is the idea. So don't make that mistake. And when we work with planes, where these bearing are problems, we normally work with bearing angle instead of reference angle because it's easier to look at something that's orthogonal from the ground rather than imagining a horizontal line. That's much harder for planes to do, to see if they're leveled or not. So bearing angle is formed from the y-axis. That's very important. Now in this problem right here, we have to draw it out. So if I wanted to draw this out, I'm going to put it up here. That way you guys can see it at the same time. I have a plane, in particular. Let's start off with the plane. It's right here. This is the starting point. And now I'm going northeast 20 degrees. So that's a bearing angle in particular. Boom. If I draw this XY axis, I'm going 20 degrees. And I'm going to use this line over here to give you the idea. And I'm going to use this in color. So boom. 20 degrees is something like this with the y-axis. With the y-axis, that's very important. Boom. So now I have, this is 20 degrees. Boom. Great. Now, somewhere along this line or whatever, the word problem states that after 200 miles an hour, after 1 hour, I make the course correction to go northeast 40 degrees. So I'm going 40 degrees. So I need to go over here. Let's suppose it's at this point right here where I start turning. I make that course correction. I need to go 40 degrees in particular. So let me do that now. Ooh, this is ugly. Let me delete that. Boom. This is about 40 degrees right here. Boom. And I should change that color actually. I can't change the color. Oh well. So 40 degrees over here. So this entire thing right here is from here all the way to here is 40 degrees. Now this is not the best illustration, but that's the idea. From here to here is 20 degrees, which means this is also 20 degrees right here. All right, the entire angle is 40 degrees, but if the other piece was 20 degrees, that means the other half had to be 20 degrees. I just didn't draw it like half, so I apologize. It's not drawn to scale. And then it's saying that then the plane in particular has trouble, so he makes an emergency landing. He stops. This is where he stops. He stops right here. Now it's asking you, what is that distance he traveled from the original position? Well, to calculate distance, it's just a straight line. This is the distance right here. Boom. Could have drawn it better, but boom. So I have this triangle I can deal with to solve for this distance. If I call this A, I call this B, and I call, oops, let me call this B over here. I call this B, then I call this C. I'm solving for beta. This is alpha distance. So the key thing is I need to know the angle measurement for angle B. Oof, that looks like a tough one, but it's not really. Think about it. I need to figure out this triangle piece right here, from all here all the way to here, that angle measurement. Well, if you notice, this line in particular is a straight line. Because it's a straight line, all these angles, this angle, this angle, this angle, and this angle have to add up to 180 degrees. It's a very strong property. Which means to solve for that missing, to solve for this peak piece right here, I just need to do 180 minus this little portion right here. Well, this portion is 20 degrees, which is very nice. It's very helpful. So I can do 180 minus 20 degrees. There are other ways you can get these values, but boom. So we get angle B is equal to 160 degrees. It's very helpful. Now I have a new triangle that I can draw instead. I don't have to use this as information anymore. I figured out that that one angle. I have a triangle that looks like this, where this is 160 degrees. And then I need to solve for beta, and then alpha, and then A, B, C. And then if I plug in the values, the first initial flight, he went 200 miles per hour. Again, this is not drawn to scale, so I apologize for that. And then after half an hour, let's see, boom, boom, boom. After a half an hour, if he keeps that same speed, half an hour later, that means he went half the distance. So that means this is 100. So you have to use your problem solving skills for these word problems to figure out the other locations. This is assuming he's going at the same speed, of course. Yeah, he's going 200 miles per hour. And now you got to solve for beta. Well, I can use law of sine or law of cosine. In this case, I can just use law of sine. It's perfectly fine. But you can use law of cosine as well to get that one unique answer. So you can solve it out and whatnot. If you try to use law of sine, you need to solve for b. So you can do sine of 160 degrees equals, this is over beta. And then choose one angle that's already predetermined and whatnot to figure out the other angle. Well, what we could do is, let's see, do I know a value? I should know a value. I guess we have to use law of cosine in this case. Law of cosine will state that we have, I want to use in particular, I want to solve for the side beta squared. So I can set this equal to alpha squared plus c squared minus 2 alpha c cosine of b, capital B. You can use that. If you plug in your values, you get beta squared is equal to alpha squared is 100 squared plus 200 squared minus 2 times, what is a big value? 100 times 200 cosine of 160 degrees. Make sure you're in degree mode, all that stuff. Calculate all of this. If you calculate it all, it should be roughly 87587.70, roughly. Beta squared is equal to that. Which means all I have to do now is square root both sides. You only get the positive answer. And this is what I mean. Cosine will give you one unique answer, which is very nice. Beta is equal to, what is that? 295.7 0.95. So that's the value of your beta in particular. All right. Now, you can for the last part find the bearing from the airport to his landing, from the airport to his landing. You can solve for that angle measurement if you would like to. But yeah, if you want to solve for the angle measurement, it's just right here. Just solve for that. You can use law of sine afterwards because you have enough pieces for your triangle to do that. Or you can use law of cosine again. Up to you. Whatever works for you. And that ends the recording. I will catch you next time. Take care.